Hello, a warm welcome to all of you guys. This is Avirup again. So today I am going to share an interesting problem which is associated with probability theory, rather the classical probability theory, or you can say the combinatorial probability theory. So the problem is the birthday problem or the birthday coincidences. So what happened in birthday problem? So the birthday problem basically asks for the probability that in a set of n randomly chosen people, at least two will share a birthday. Okay, so the birthday paradox basically refers to the counterintuitive fact that only some of the people are needed for that probability to exceed a particular percentage. That is, you can say if 23 people are needed for that probability to exceed 50%. Okay, so let me write the things that what is the motivation of the, or what is the main, in what context we deal with this birthday problem. Okay, so the birthday problem basically asks the birthday problem asks for uh, so actually my handwriting, I don't know why this is so for the uh, probability that in a set of n randomly chosen people, in a set of n randomly chosen people, at least two will share a birthday. Okay, that is, the birthday paradox basically refers that the birthday paradox, so this is a paradox. Okay, so what is paradox? So I will attach a link in description, or you can say the comment section, so that you can go through that, the idea of paradox, or what does the paradox mean to us. Okay, so, or birthday coincidence, you can also say that it refers to the counter intuitive okay counterintuitive fact that if n equals to 23, okay, three people are needed for that probability to exceed 50%. Okay, so this birthday paradox, it sometimes seems wrong at the first glance, because uh, I mean, in fact, true, but while it may seem surprising that only uh, 23 individuals are required to reach a 50% probability of a shared birthday. Okay, so this result is made more intuitive by considering that the birthday comparisons will uh, be made between every pair of individuals. Okay, so with 23 individuals there are okay, so 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 with 23 individuals there are say suppose 23 times 22 over 2, that is 253 pairs, okay, to consider. So for the more than half the number of days in a year. So in a real world application for the birthday problem include uh, say cryptographic attack called the birthday attack, which uses this probabilistic model to reduce the complexity of finding a collision, okay, for a particular entity, as well as calculating the approximate risk, okay. So the problem is that, so how do we deal with from the uh, mathematical perspective, okay, from the mathematical uh, things, how it constructed. So you see uh, that so from a permutations perspective, if you know that what does permutation mean, and I hope you heard this term permutation and combination. So this is the basic combinatorial concept, and maybe in 11th or 12th standard you have already come across with this concept, that how we deal with from the very mathematical perspective. So if you just forgot these things, so I will suggest that once revise. So from a permutation perspective, if we assume that let the event A be the probability of finding a group, okay, a group of 23 people without any repeated birthday, any repeated birthday, okay. Okay, now repeated birthdays. So where if I take another event, okay, say where say another event where B, the event with at least two people sharing same birthday it could be possible, right? So what will be the idea, or how can we write this? So the probability of B will be 1 times, not 1 times, this is 1 minus probability of A times not times, yeah, probability A, 1 minus probability A. So this probability of A, this probability of A is what? This is probability of A is the ratio, okay, the ratio of the total number of birthdays, ratio of the total number of birthday correct. uh, so uh, we can we can also do another way, okay. uh, okay, so let us take some another notations take. So this notation, this is a typical, not typical, so uh, mhm. So if we take permutations, or the notation of these, something like uh, P, capital P in R, okay. uh, so maybe I could be wrong. So P in R, or not P, don't take P, say, okay, let take it P in R, or you take V, okay, this in R, okay. So without, that is without repetitions and order matters, okay, order matters. So we can also take an example like the for a group of two people, like the birthday, this pattern MMDD, okay, birthday, this format, birthday format, okay. uh, one possible outcome could be this, say suppose 0 1 0 1 0 2, okay, this comma 0 5 2 0, okay, and so like this. So this is a possible set. Again, uh, 0 5 comma 0 5 20 comma 0 1 0 2, okay, and so on like this. So if we divided it by the total numbers of birthday with repetitions and order matters, okay, so so let us write like so divided by outcome is so this outcome, and it is divided by is divided by the total uh, is okay is divided by the total number of birthdays with repetition and orders matters, okay, that is VT. Now as it is the total space of outcome, okay, as it is the total space, is it okay, space, um space, yeah, total space of outcomes, okay, from the experiment, that is that example, that two people one possible outcome, okay, experiment, which is uh, two people one possible outcome is this 0 1 comma 0 1 0 2, okay, that as I said, MMDD birthday format 0 2 uh, 0 1 0 2 like this, and 10 0 2 and 0 8 0 4 like this, and it will continue, okay. So therefore you see this VNR and this VT are permutation, okay. So we can write this VNR, this n factorial over n minus k factorial, which is 365 factorials. Okay, 365 minus 23 factorial. Okay, and this VT, okay, whereas this VT is nothing but n to the power k, that is 365 to the power k, and where this k equals to 23. So we can take this as k randomly chosen people, or okay, it is okay with the n. It's right here n. Okay, fine. So it is okay, okay, fine. So yeah, don't jumble up notations. Okay, so this is I have just written for general purpose to understand, but in solving problems, don't jumble up or mixed up these notations, otherwise everything will be so you will be confused. Okay, fine. Okay, now, so if I take the probability of A, so probability of A will be VNR over VT, as we say that probability A is the ratio of total number of birthdays, so it will be like this. VNR, you know the VNR, so you compute from here and you compute from this, so it will be approximately something 0 point, actually I have previously calculated this, so you see this is 0.492703 like this. So now probability of B is 1 minus probability of A, that is 1 minus that 0.492703, and it will be, so I'll use this approximate sign here. Okay, so as, okay, and this will be like 0.507297 like this, so that is 50.729, this percentage it will follow, right? So see, this is one way of dealing with this, but maybe this idea cannot be shared in school and college. I don't know why. So if you think like this, or if someone has already shared this way, so I appreciate, but I love this way to explain. But another way the birthday problem can be solved is by asking for an approximate probability that in a group of n people at least 2 have the same birthday. So for simplicity, the leap years, twin selection bias, and seasonal and weekly variation in birthday rates are generally disregarded. Okay, and instead it is assumed that there are 365 possible birthdays. Okay, and that each person's birthday is equally likely to be any of these birthdays, independent of the other people in the group. Okay, so for independent birthdays, the uniform, so if you heard about uniform distribution, so I shouldn't talk about distribution perspective, because I am not sharing something called birth distribution things. But if you little bit heard about uniform distribution, for those it will be helpful to understand that uniform distribution on birthdays is the distribution that minimizes the probability of two people with the same birthday. Okay, so the problem of non-uniform number of birthdays occurring during each day of the year was first addressed by uh, uh, I just forgot the name. So there's a people say who there is a man, there is um a mathematician, okay, who shared this, who addressed this. So as it happens, the real world distribution yields a critical size of 23 to reach 50%. So the goal, I'll write, the goal is to compute probability of A, this probability of A, and you know the what I have addressed, this A, event A. So the probability of A, so the probability that at least two people in the room have the same birthday. Okay, however, it is simpler to calculate, so it is simpler to calculate probability of A complement. Okay, the probability, sorry, the probability that no two people, the probability that no two people in the room have the same birthday okay, then because A and A complement are only two possibilities, so I'll write, then because A and A complement are the two, the only two possibilities and are also exclusive. And you know this, what does mutually exclusive means? Mutually exclusive, that is why probability of A equals to probability of A equals to 1 minus probability of A complement. Okay, so here is the calculations of probability of A for 23 people. Okay, now so probability of A for 23 people. Okay, so let the 23 people be numbered. So 23 people, let 23 people be numbered 1 to 23. Okay, so the event that all 23 people have different birthdays in the same as the event that person 2 doesn't have the same birthday as person 1. Okay, and that person 3, okay, that person 3 doesn't have the same birthday as either person 1 or person 2, and so on, and it will continue like this. So and finally that person 23 doesn't have the same birthday as any person 1 through 22. Okay, so this is the logic. So let these events be called event 2, event 3, and so on. So event 1 is the event of person 1 having a birthday which occurs with probability 1. So this conjunction, so I am just saying, so whenever you will see this recording, so try to understand the logic. If you trying to note it down something as what I am saying verbally, just pause and try to understand the logic behind it. So again I am repeating that the event that all 23 people have different birthdays, that is the same as the event that person 2 doesn't have the same birthday as person 1, and that person 3 doesn't have the same birthday as either person 1 or person 2, and so on. And finally that person 23 doesn't have the same birthday as any of persons 1 through 22. So these events be called event 2, 3, 4, 5, and so on. So event 1 is the event of person 1 having a birthday which occurs with probability 1. So this conjunction of events may be computed using conditional probability. Okay, so what is the conditional probability formula? So probability of A given B is, so as given B means B already occurred, so it will go to denominator. So probability of B. Now probability of A intersection B. Okay, so this is the formula of conditional probability. Okay, so using conditional probability, so the probability event 2 is so the probability of event 2, the probability of event 2 is 364 by 365. Okay, as person 2 may have any birthday other than the birthday of person 1. Similarly event 3 event 3 is 363 over 365, right? So as person 2 may have any birthday other than the birthday of person 1. So similarly probability of event 3 given that event 2 occurred is 360. Okay, no, maybe I have made something wrong. wait. Yeah. So yeah, correct. So the probability of event 2 is 364 over 365. Okay, so as 2 may have any birthday other than the birthday of person 1, similarly the probability of event 3 is uh, event 3 given that event 2 occurred, okay, is 363 over 365. Okay, so as person 3 may have any of the birthdays not already taken by person 1 and 2. Okay, so this will continues until finally the probability of event 23 given that all preceding events occurred is that is 343 over 365. Okay, so finally the principle of conditional probability implies that probability of a complement, okay, is equal to the product of these individual probabilities. So how do we write this thing, or how do we construct this? So probability of a complement, so this is the logic, try to so previously whatever I have just justified, so try to grab the logic. So without logic it won't be constructed. So probability of a complement, that is 365 over 365, that is 1, you know. So so this is 364 over 365, 363 over 365, and it will continue up to 343 over 365 like this. Okay, so this is probability of a complement. So let us give this 1. Okay, and you see that probability of a complement is 1 over 365 over 20 raised to the power 23 and multiplied with 365 up to 343, right? So this is 2. Great. So if you evaluate the equation 2, so it will give you that approximately 0.49 270 wait 0.4927 and so on. So therefore probability of A is 1 minus 0.49 2703 is approximately 0.507297. Okay, this is nothing but 50.07 50.7297%. Okay, so this process can be generalized to a group of n people. Okay, so this process can be generalized to a group of n people. Okay, where where probability of n is the probability of n is the probability of at least two people. Okay. um, so let me write this, where p of n will define um, as, so n people. Okay, so it will be at least the probability of at least two of the n people, sharing a birthday. Okay, so it is easier to first calculate the probability. So easy, so it is easy to calculate the probability. So it is say this so let's p bar, I am using p bar n. So this p bar n, that all n birthdays are different. So all n birthdays are different, right? So according to pigeonhole principle, so what does pigeonhole principle mean to us? Okay, so we'll use the pigeonhole principle in this case. So what does pigeonhole principle? So let me go to the next page. So in the context of combinatorics, the pigeonhole principle states that pigeonhole principle, so pigeon, pigeonhole principle, simple. Okay, so what does this pigeonhole principle states? That if n items are put into m containers, okay, m containers with n greater than m, okay, then at least one container must contain more than one item. Okay, so for example, say 3 gloves, none of which is reversible. So at least 2 must be right-handed, or at least 2 must be left-handed, because there are 3 objects but only 2 categories of handedness, two categories of handedness to put them into. So this seemingly obvious statement, a type of counting argument, can be used to demonstrate the possibly unexpected results. Okay, so you see, one more thing I want to share, that is, so if you see this image here, so I am putting this image here. So you see this image. So there are 1 2 3 4 5 6 7 8 9 pigeons. So here are the n equals to 10 pigeons in M9 holes. So 1 2 3 4 5 6 7 8 9. So here this is nine holes, and you see the 10 pigeons are there. Okay, so here uh, uh, there are n equals to 10 pigeon. I'm sorry 10 pigeons in m equals to 9 holes. Okay, since 10 is greater than 9, as 10 is greater than 9, so the pigeonhole principle says that at least one hole has more than one pigeon. So you can see here so here there is one more pigeon is placed. Okay, so this is the idea of pigeonhole principle. Okay, so we can do several kind of problems, combinatorial problems, and we can also use this pigeonhole principle solving the combinatorial problem, the combinatorial probability problems. Okay, so this is a very nice concept. Okay, so so let us go back to our main problem, which is, so if we compute the probability uh, of probability n bar probability sorry this I'm sorry so this, so if we compute this, so it will be 1 times 1 minus 1 by 365, okay, times 1 minus 2 by 2 over 365, and if we continue like this, so it will be 1 minus n minus 1 over 365. Okay, so if we do so, it will be like 365 times 364 times dot 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 up to 365 minus n over plus 1 over 365 365 to the power n, which is equals to 365 factorial over 365 to the power n times 365 minus n factorial. We can more generalize the things. How we can generalize? That is, n factorial 365 can, so n can be chosen like this, 365 to the power n So we can write this as uh, the permutation, that is 365. Use the permutation notations. So this is P 365, sorry 365 over n, and 365 in you can say the power, or and this n is in suffix, and 365 to the power n, like this. So where this factorial is the operator and 365 choose n is the binomial coefficient, and this p 365 pn is the permutations. So this equation express the fact that the first person has no one to share a birthday, the second person cannot have the same birthday as the first, uh, the third cannot have the same birthday as either of the first two, and in general nth birthday cannot be the same as any of n minus 1 preceding birthdays. Okay, fine. So the event at least two of the n persons having the same birthday is complementary. Okay, uh, to all n birthdays being different. Okay, so we can as I do R programming, being a probability and statistics student, I do the R programming. So I have modeled these things out using programming. I have written some code. Okay, so I can share this code with you guys. So just wait for a while. So let me connect this. So let me so just wait for a while. Yes, it's opening. It is opening. Just yeah. So I have written some code to make you understand that the visualizations, I mean how the things are computing. Okay, so here it is saying that we need to install something, install the DT package. So I hope it is installing. Um, okay, so fine. So it is I have modeled the number of people in room. Okay, so for the that is k equals to 100. Okay, so you can choose as per your requirements. So this is k equals to 10, sorry 100, and the number of people in room is 100. So now what I have did, so I have create a numeric vector, that is p, where all the k values can be stored. That's why I have provide a command line that create a numeric vector to store all the probabilities. All the probabilities which will compute will be stored in p. So I have assigned a numeric k, and now I have executed a for loop. Okay, so which is I running 1 to up to k. Okay, and q is the that is the probability at that b event, or something like 1 minus probability of event A, that is the thing basically. So, and which is divided by 365, that is the 1 minus probability of no matches. So this line, you can see this number 4, line number 4, that is 1 minus probability of no matches. Okay, and this probability of I is storing all 1 minus probability, the all the product. Okay, so you see this mathematical things over here, that this product I have writing here. So this is something like that. So let me write is 1 minus. So storing out that thing. Okay, so storing out that thing, I'm using. So now what I have did, so to probability at least two people have same birthday, I have so I have plot these things out. So if you so if we run these things, entire things, and so control enter, and you see, so let me zoom these things out. So you see, so this is the probability at least two people have same birthday, and this x coordinates is number of people, and as the number of people increases, the probability also increases. Okay, and it increases like so you see this, if it is somewhere 23, so it is going to 0.5 towards 0.5. Okay, so I mean the 50% is going to compute. Okay, so let me take a screenshot of this. Okay, so this is a nice visualizations. Okay, so let me take the screenshot properly. Yes, so this probability, I'm sorry, so this probability, so these are nice visualizations, I would say. Sorry, I don't know why it is problem. So yeah, now it is properly, it is taking the screenshot. So let me save this out. Yes, so let me go back to our code again. So now what I have created again a vector. So and create so number of people 1 to up to 100. Okay, and I have created another vector, say probabilities, and it will store all the probabilities, and this probes, under this probes, in the line 12, this combine into a column wise bind all the number of people and probabilities, so that you can understand that if whenever this number of people increases, how the probability is going to vary. So now I'll execute, and I have created an output table which is called the data table. Okay, so if I just run this, so you'll see how beautiful it is. So control enter, if we do execute this, so if we zoom this thing again, so you see, so this is the table actually. So as the number of people increases, so 1 2 3 4 5 6 going, and how the probabilities is going to vary, and showing 1 to 10 of 100 entities in the first page. So next page, so this is 11 to 20 of 100 entities, and you see how it is approximating the things. And if we go to third page, and you see this 23 cases, how this probability is going to change, and this is, and we have calculated right thing, that is 0.5073 like this. Okay, so this is how we are going to approach for a probability perspective, and we can model our mathematical things into a to simulate our ideas of probabilities. So I have tried my best to elaborate this concept and elaborate this problem in a from a ground basis, from so maybe some sort of concept you need to revise once, and this problem too. So let me go back to the this here. So this is how the things varies. So let me arrange these things properly. Okay, so okay, sorry. So this is the thing. Okay, sorry. So let me cut this thing out, and well, you can practice more problem like this. So if you like it, so as this things is very interesting. So you can study detail. There are a lot of consequences which is attached with this birthday concept. Okay, so if you want to know more about this birthday consequences, so please uh, let me know in chat section, and do study more about this birthday things, not birthday things, the mathematics probability, whatever you like most. So this is the image I want to attach here for further understanding. Okay, so yes, yes. Okay, so this is an wonderful session. I have really enjoyed to teach this birthday problem from mathematical point of view and model these things out to simulate in a programming environment. So I have used R. You can also use Python or MATLAB or anything you want. So for this session, I am going to end to say that uh, thank you for listening, and thank you. So do enjoy to uh, to encounter more challenging problems, probability, statistics, pure mathematics. So you can let me know in chat section that what type of problems you are expecting to solve by me. So thank you for this um, patience. If you really do study these things, it will be honor for me. uh, thank you.